The central limit theorem gives us a way to make probabilistic statements about the sample mean. Usually, what we know about the population is limited to our sample, so it's good to know that the sample mean has this property where if n is large enough, we can assume it's normal. Remember, if I have a normal random variable, and I subtract mu and divide by sigma, I have something that follows a standard normal distribution. The sample mean follows this distribution here. The sample mean minus the population mean divided by the population standard deviation divided by the square root of n follows a standard normal distribution, which has mean 0 and standard deviation 1. This is important for what follows. One problem with our approach so far is that the sample mean follows this normal distribution that depends on the population standard deviation sigma. If we don't know mu, why would we know sigma? Up until now, we've just assumed that we knew sigma and neglected it. But the last step to being able to make inference about a population mean based solely on the information from our sample is to get rid of this sigma. And that's what we'll do today with the t-statistic. When you're doing a hypothesis test, you assume that mu equals some value, and your reference distribution is centered at this hypothetical mean. A proportion is a type of mean, and it can be shown that when the population proportion is p, the standard deviation of the population, sigma, equals the square root of p times 1 minus p. Because this sigma is based on p, this is the one time you will know sigma, because you're assuming that p is the true parameter, so you can assume that sigma equals this. In most other cases, though, you won't know sigma. Instead of trying to make assumptions about it, you just replace the sigma with the sample standard deviation, s. But now, this thing follows a standard normal distribution. When you replace the sigma with s, it doesn't follow a standard normal distribution anymore. It follows what's called a t-distribution with n minus 1 degrees of freedom, where n is the sample size as usual. There are infinitely many t-distributions. When n is large, there's not much difference between a t-distribution and a standard normal distribution. They're all centered at 0, but the t-distribution has these higher tails and a lower peak. As n gets bigger, the t-distribution gets closer and closer to a standard normal distribution. The two assumptions we need for the t-test are independence and normality. For independence, we rely on the fact that we're taking a random sample of something. So whether an element from the population shows up in the sample is independent of any other element's appearance. Identically distributed essentially means we're drawing them all from the same population. So we're not drawing some of them from a normal distribution and others from a uniform and then others from a right skewed distribution or something like that. They're all coming from the same distribution. The t-test assumes that the sample mean has a normal distribution. If the population itself is normal, then the sample mean will always be normal. If the population is not normal, then the central limit theorem says that the sample mean will be approximately normal when n is greater than or equal to 30 or so. So as long as your sample size is greater than 30, this test should still work. If your sample meets these criteria, you can use the t-test to decide hypotheses concerning the population mean. To perform a t-test, we compute a t-statistic and compare it to a t-distribution. The commands we use for a t-distribution are pt, qt, and dt. They work the same as the corresponding normal commands, but with the t-distribution, the only parameter is the degrees of freedom. These don't take a mu and sigma argument like the normal commands do. Here's an example using the trees dataset from R. Let's say we want to test if these trees come from a population whose height is different from 78 feet. The sample mean we got is 76 feet. That suggests maybe the population mean is lower, but we can use the t-test to make a decision. First, I don't know how these trees were collected, but let's assume they're a random sample from some larger population so that our independence assumption is met. N is 31 here, so we can use the central limit theorem. We won't worry about whether the population is normal or not, but in practice, you would at least check the sample to see what it looks like, because if it's really skewed, maybe you would want to use the median instead of the mean anyway. But we've satisfied the conditions for the t-test. Our null hypothesis is that the population mean is no different from 78. Our alternative hypothesis is that the population mean is not 78 feet. This is a two-sided test. We'll look in both directions. The first step is to calculate the t-statistic. When you have the sample, you know everything you need to calculate this thing. You have the sample mean, the sample standard deviation, and the sample size. You don't know mu, which is the population mean, but we assume that mu equals 78 under the null hypothesis. So we do have a value for mu when we assume that the null hypothesis is true. The t-statistic is negative 1.7476. This statistic will follow a t-distribution with n minus 1 degrees of freedom, where n is the sample size. Here, n is 31, so the degrees of freedom are 30. We compare this to a t-distribution with 30 degrees of freedom. The t-distribution is always centered at 0. When you're doing a two-sided test, you look at where the t-statistic landed on the distribution curve. Then you calculate the area that would be more unlikely than what you got, and finally double it to get the area on the other side. The t-statistic is negative 1.7476, which is here. The area that's less likely than what I got is this area here. And then to get the p-value, I can double this because the t-distribution is symmetric. Note that the reason this statistic is negative is because my sample mean was lower than my hypothesized mean. If the null hypothesis is correct, then the sample mean is lower than the population mean, and the t-distribution describes how unlikely that sample mean was. The sample mean was 76. If it had been 75 with the same sample standard deviation and size, the t-stat might have been here. If the sample mean was 74, the t-stat might have been here. So that's why this area is considered less likely than my result under the null hypothesis. If the true mean is 78, drawing a sample mean of 74 is less likely than drawing a sample mean of 76. Because I'm doing a two-sided test, I have to consider values just as extreme on the other side as well. If the population mean is 78, then drawing a sample mean of 80 would be just as unlikely as 76. and a sample mean of 81 would give me a t-stat maybe over here, and that's even more unlikely. Because we're concerned with any values that would give us evidence of a difference from 78, we have to account for the area on both sides. I use the PT command in R to get the area. The P commands in R always give you the area behind the statistic on the curve. This is finding the area behind negative 1.7476 for a T curve with 30 degrees of freedom. And then I double that to get the area for both sides. R has this t-test function you can use, but this only works if you have the actual data. If you have the summary stats like the sample mean, standard deviation, and sample size, you would have to calculate the t-stat yourself and use the PT command. The confidence interval for a t-distribution is found just the same way as with the standard normal distribution. It's an inversion of a two-sided hypothesis test. And it corresponds to a two-sided test in that if your hypothesized mu is in the interval, you fail to reject the null hypothesis. If mu is not in the interval, you reject the null hypothesis. S divided by the square root of n is called the standard error of the sample mean. You multiply the standard error by this critical value from the t-distribution with the appropriate degrees of freedom. The critical value depends on your interval. If you want a 95% interval, the critical value will be the 97.5th percentile because you want the middle 95% of the distribution. You want the area from the 2.5th percentile to the 97.5th percentile. If you wanted a 98% interval, your critical value would be the 99th percentile because you would want the middle 98% of the area, which goes from the first percentile to the 99th. You can get this output from R's t-test function, but make sure you're always doing a two-sided test to get a confidence interval. Let's say I wanted to perform a one-sided test to see if the population height was less than 78 feet. Then everything works as before, same t-statistic, same distribution, except that my p-value is only half what it was before, because under my alternative hypothesis, values considered as or more extreme than what I got are only the values less than or equal to my t-statistic. If my alternative was that the population mean was greater than 78, then values more extreme than my test statistic would be everything higher than the t-statistic I got.